Hello, everybody, and welcome to episode 89 of I Wish You Were Dead, a podcast about things that used to be alive. My name is Gavin. That is Fia. Mike is still adventuring. He unfortunately didn't send us a thing this week. Hopefully, he is still alive and kicking. I should really text him. Uh,
Yeah.
those memes. I should call her. I should call him.
We should call him, hopefully, still alive.
Yeah, I mean, I think I've seen him posting stuff on Facebook, so I'm 99% sure he's still alive. But schools resume in New York next week, so I know at least next week he will likely not be adventuring. Whether or not he'll want to join us with starting his job back up, who's to say? But next week we have a really exciting topic. As we announced last episode, we're announcing the next episode's topic, the week before. So next week is a multiple of 10, episode 90, which means it's a Fia episode.
Woohoo!
So Fia, what are we talking about next week?
Yeah, I'm not going to get into too much, but we are going to talk about the Isles de Jean Charles. I have no idea if that's how you pronounce it, but that's how I'm pronouncing it. And
Okay.
it'll be a little bit of a surprise.
Interesting. I like it. But yeah, so that'll be interesting. And then do you have any other announcements for us today, Fia?
Yes, you bet I do. Do not forget to follow us on Twitter, Facebook, and YouTube to give us feedback about the show and any future topics you would like to hear on the podcast. And also, if you would like to be a guest on the show, hint, hint, maybe Andy, be sure to fill out our guest form, and that can be found in the show notes.
Awesome. And I guess we're really front-loading Fia a lot this episode because that brings us into our Swamp Corner.
Yes,
So
here
Fia,
I am.
We're trying to coordinate a little bit better about trying to make Swamp Corner a little more, like, I guess less random relative to the episode topic. And
Right.
this is a hard episode topic to find something for.
Yes,
So I
I
don't
have
blame you.
learned that. Yeah.
But you're talking to us about a bivalve today, and we will talk about some bivalves later. Spoilers. So what do you got for us?
Yep. So I have Mycella planulata, but I guess that's the name I know it as. Apparently that's wrong, and it's Curdiella plantulata. I guess name change, taxonomy. Also known as the Atlantic flat lepton. I've never heard it
So
called that.
I can comment on the name change a little just by looking at it here. So when the genus changes but the species name does not, that means that someone was like, this species better belongs in this other genus, but because of how taxonomy works, you can't name it a new species, and because the original species it's called having precedent, it was named first, so you just give the new genus. Or sometimes if someone is looking at that particular species, they think it's different enough to put in its own genus. Instead of putting it in a pre-existing one, they'll make a new one for it if it's different enough. And in that case, the species name also has precedent, so the genus will change, but the species will not.
Very cool. I did not really know that, but thank you. So I guess we have a little genus change. This is not quite a brachiopod, but a close bivalve. And spoilers, we will be talking about brachiopods later in the podcast.
We sure will.
They are found all over the Atlantic, Gulf of Mexico, Caribbean Sea. They're believed to be suspension feeders, probably feeding on organic matter, which makes sense given that they're bivalves.
Right.
The cool thing that I found out about these little guys is that they are simultaneous hermaphrodites, which means that an individual has sex organs of both male and female and can produce both gamete types simultaneously. And that means also that they are capable of self-fertilization. And in an article that I read about them, they said that seemed to be the more common way of reproduction instead of releasing sperm and cross fertilizing with other individuals.
Interesting. I have a couple questions.
Yes.
Um, are most bivalves not hermaphroditic?
Um, Most bivalves, I believe, that don't. I can't quote too many bivalves,
Okay.
but
Yeah.
they are hermaphroditic. There's two types of hermaphrodite uh, types. There's simultaneous, and then I forgot the name of the other one, but it's when you change, like it's like an on-off switch,
Oh, okay.
where like you're either male or female. But this one is kind of a subset where like they can do both switching on and
Mm-hmm.
off, or they can fertilize themselves as like
Oh.
simultaneously, I guess,
Mm-hmm.
if that makes sense.
Because so the interesting that they prefer to self fertilize. That's
Right. I thought that
interesting.
that was weird too, because that's not really like great for like keeping the population going if there's like
Right.
big wipeouts of like stuff due to like weather or temperature, like environmental variables, I guess. But
Right. And so it is much less efficient at creating new like combinations of
mhm,
genes,
yep,
but it still in theory can be fine. It's just very unusual.
right. And that's why I thought that that was kind of cool for this guy.
Yeah, neat.
Unique.
Invertebrates are so weird.
They are.
I'm sorry.
They are very weird.
we
But
we
that's why I
sure will
love
be
them.
talking. Yeah, we'll be talking about quite a lot of invertebrates today. Mostly how they die. Spoilers. Um, because so is that all you've got for us for Swamp Corner?
Yes. Yep,
All
that's
right.
it.
So speaking of a lot
What do
of
you,
invertebrates dying, today our main topic is the Permian period, specifically the End-Permian mass extinction, which, spoiler alert, is the worst mass extinction in at least the last like 600 million years, if not the entire history of Earth. We'll talk more about all of that wonderful happiness as we get through the episode. But the Permian period, and I actually just bought a new pop filter for my microphone because I knew that I was going to have to be saying Permian period a lot in this episode. So the Permian period lasted from 298 to 252 million years ago. So in the grand scheme of complex life on Earth, it's about in the middle from
okay.
the time we had the Cambrian period, way back in somewhere in the ballpark of starting around 540-ish million years ago, and then going through till today.
I have a question.
Yeah.
How do you remember the uh, periods in sequential order in your brain? Like, do you have like an acronym or like just like repetition that you use to remember like all of the periods?
There definitely are mnemonic devices. I don't know any. That's just something that one if you've I had a so there's the the like main chart that you'll see of all the geologic time periods. It's called it's usually put out by the Geological Society of America. It's usually you can just Google like stratigraphic chart or
Mhm.
something, and or geologic time scale. Either will come up. And I had a sticker of it. I went to a Geological Society of America conference a couple years ago, and they were giving out free stickers of the most
Ooh,
recent version at the time because it gets updated a couple times a year. And I put it on my water bottle that I used every day because I was still an undergrad, and I'm like, I really need to know this.
wow.
So every time that I would take a drink, I would like look at it and sort of quiz myself. Um, remembering them in order isn't necessarily the hard part. Remembering the dates is much harder, which I only actually know because of the podcast.
Nice. That's a really cool thing that they were giving out.
Yeah.
And a good way for you to learn.
Yeah, for sure. But yeah, so it was very handy and a very useless skill that I have now. So, the Permian period, like I said, in the ballpark of 300 to 250 million years ago. And the Permian period is fairly unique. It has something in common with only one other geologic period, and that is it is the end of an era, literally. So, a brief refresher of geologic time. We talked about geologic time in much more detail way back in episode 22, but the way we break down geologic time is in different sized chunks. So, the biggest ones are eons. After that is era, then period, and then epoch. And then even within there are smaller ones, but those are the only ones that most people have heard of. So the Permian period is the final period in the Paleozoic era. So whatever happened at the end of this guy was significant enough for people way back in the day, because all of the periods were mostly named and all the boundaries were mostly defined before we knew of all these different mass extinctions, or even had like good numbers to put to the time for these periods. So even way back before we knew about the mass extinction, early paleontologists knew at this line in the rocks, you see a lot of stuff here, and then almost nothing for a little bit afterward. Okay. So this was a big deal. But as per usual, before we talk about the actual extinction, we got to talk about what the world was doing, how the world was looking before. And the Permian is really famous for having fairly large oil reserves. For example, a lot of the oil in Texas comes out of what's called the Permian Basin from this time period. Lots and lots of cool animals running around that we'll talk more about in a little bit. But it's most famous for two things.
Are you talking about oil reserves like today?
Yeah.
Like you can still find these today? Oh, cool.
Oh, yeah. Yeah, like most of the oil currently being drilled in Texas was deposited during this time.
Very cool.
So the Permian period, very famous for lots of things, but two things mainly. The first is this is sort of the main time of Pangaea, when all of the continents came together to form the continental megazord of Pangaea. That was mainly around this time. Pangaea formed in the Carboniferous period before this and broke up toward the end of the Triassic period after this. So this was the main time of Pangaea being fully together. And also, as I've said several times, this period is home to the worst mass extinction in the history of Earth, with a slight asterisk. And things were just really funky on the planet thanks to Pangaea. This was the only time that we've had a supercontinent where there was life on land. And so life on land reacted really weirdly. Not to mention, a supercontinent is just a fairly rare thing in Earth history. So it just kind of messes with some of the normal Earth processes.
And is there like a reason why, or just like chance of luck that like life on land just happened at this time?
So life, when certain things happen in Earth's history, don't necessarily always have a particular reason. But the previous supercontinent before Pangaea was breaking up around the time that like complex life was getting started.
Okay.
So it just never lined up properly.
Yeah. But the stars have aligned in this situation.
Exactly. So, like I said, Pangea fully forms in the Carboniferous period, which we talked about in episode 81. Carboniferous period, really weird period at the beginning and sort of through the middle. Very lush, basically global rainforests. But then when Pangea formed, and for a variety of other, weird chemistry, climate reasons, things got very, very dry and much colder. All those plants sucked a bunch of CO2 out of the atmosphere. And as we've talked about several times on the show, as well as if you watch the news, you probably know that CO2 in the atmosphere raises temperatures. So that if you suck CO2 out, it decreases temperatures. And so with global rainforests, they were just pulling so much CO2 out of the atmosphere that they caused pretty much a cold snap that then killed off some of those rainforests. And then also, when a supercontinent forms, the land gets generally much drier. So think about places like the middle of North America, for example, the farthest you can be from the ocean on North America. And I'm only using North America because that's where we are from, and we're biased. So like I lived in South Dakota. South Dakota is a very dry place. Just because it's so far, no matter which way the wind is blowing from, by the time it gets to the middle of even just a regular sized continent like North America, all the moisture has dropped out of it. And that is especially the case in, when you have a supercontinent, because it just has so much farther to travel with that water that all of it just falls out. So the middle of Pangea was a giant desert.
And
But yeah.
So how does groundwater fit into those situations? Like, does that make a difference at all to the dryness?
Not really, because groundwater is replenished from rainfall.
Okay. Okay, I see. Yeah.
Yeah, so if it's not being replenished, it will the water table will just continue to sink farther down.
Gotcha. All right, that makes sense.
Yeah. But there were also some other kind of interesting things going on because of Pangea. So if all the land is together, that inherently means all of the ocean is together. So meanwhile, where there's one giant continent, there's also one giant ocean called Panthalassa. And unfortunately, we don't have great rocks from Panthalassa just because oceanic rocks get recycled fairly frequently. And so the oldest oceans are younger than this, oldest oceanic crust. So we don't have great records, and we don't super know what was going on in a lot of the deeper parts of Panthalassa. But in some of the more shallower areas, we actually have a pretty good idea of some stuff that was going on, especially the fossils. We have lots of really good marine Permian fossils. But because there's less coastline, if North America has, a coast on either side, if, the East Coast was over connected to Europe, that gets rid of half of North America's coastline. So when all the continents are together, yeah, there's a really big coastline all the way around the supercontinent, but overall less coastline and less shallow marine areas. So it's a little bit counterintuitive, because you think all the continents are together, that should make one big coastline, which it does, but just sort of how if you break something up, if you pound up some or break up sugar into smaller pieces, it'll dissolve faster because there's more surface area. A similar sort of thing there.
Right.
And curiously, I had always been kind of told that the Permian period was actually quite hot, which would make sense because, it's very deserty. We tend to associate deserts with being really hot. But the more I kind of looked into it for this episode, the Permian period actually had temperatures fairly similar to today. So,
Okay.
There were ice at the poles, especially at the South Pole, because Pangea was mostly in the southern hemisphere. Less extreme temperature differences between the equator and the poles than we have today, but still pretty notable relative to certain other times in Earth's history. And while the beginning of the period was quite cold and glaciated, going from the Carboniferous into the Permian, things get quite a bit warmer, especially toward the end. We'll talk about that in a sec. And so all of those glaciers that were present at the beginning of the period sort of retreat to the high mountains and to the very, very South Pole. And lastly, lots of volcanic eruptions going on, especially in the late Permian, that also help increase the temperature. Once again, more on that later.
Okay.
So that's what global, what the planet itself was doing. But let's this is a paleontology podcast. Let's talk about what the actual life was doing. And the oceans were very classic Paleozoic era. Throughout the entire Right. So throughout the entire Paleozoic era, a handful of groups filled most of the niches in the ocean. So brachiopods filled pretty much every benthic sessile filter feeder niche. Bivalves were around, but were less prevalent. For more on brachiopods, listen to episode 68. Crinoids were also generally benthic sessile suspension feeders, but they were elevated up off of the sediment because they have a long stalk. And
what are the crinoids look like again?
So they're more colloquially called sea lilies.
Oh, they have like fans, kind of.
Right. So they're sort of a starfish, but flipped upside down and with a long stalk that connects it to the ground. So whereas things like brachiopods and bivalves sit basically right on top of the sediment while they're filtering their water, crinoids elevate themselves up off the sediment so they're not competing with those other filter feeders.
Very cool.
There were a couple different kinds of corals, very different corals than we have today. There were solitary corals that could be like as big as like your hand, called the rugosan corals, and then some more encrusting, more familiar looking corals called the tabulate corals that sort of build themselves up in layers differently than the modern corals do. Modern corals did not exist at this point in time. Various different kinds of mollusks, mostly things like nautiloids, which are sort of the more primitive, I guess. I don't really like that term, but the earlier version of the swirly shelled squid boys. So instead of, if you've ever seen Omanite, the Pokemon, that, but swimming around in the water.
Nice.
Yeah. And lastly, trilobites. So trilobites weren't doing great by the Permian. Both of the previous mass extinctions in Earth history really hit them pretty hard. But they were still around. So those groups make up really the main parts of all the Paleozoic shallow marine ecosystems. But especially, they do they have a very high degree, these ecosystems, of tiering. So we'll have things at various levels throughout the sediment. So things could be very deep inside the sediment, relatively shallow in the sediment, everywhere in between. Things sitting on top of the sediment, things elevating themselves up off the sediment, and then things swimming up through the water column. And this level of ecological tiering goes away. It is at its highest time here, and still to this day is not to the point that it was in the Permian period.
Dang.
Yeah. And overall, things were doing all right. They were struggling a little bit throughout the period just because there were less of these shallow marine ecosystems to inhabit. Up on the good old dry land, very dry land in this period, plants were doing some cool stuff. In the Carboniferous period previously, gymnosperms, the conifers, first evolved. So these would be things like your pines, your cycads, things like sequoias, ginkgos, things that put their seeds in cones. They were doing great. because those kinds of plants are really good at living in dry places. That's
Mm.
Those are some of the ecosystems that they lived in the Carboniferous. So they were kind of restricted to the very high altitudes. So like more up in mountains, because there just wasn't enough rainfall for the rainforest that occupied the rest of the planet. So that's sort of where they got their start. And then once the rest of the world dried out, they were like, yes, this is my chance.
So I'm a little confused. Can you explain like why they would do better at higher altitudes? Like you're saying
Uh,
in mountains?
yeah, just because it's drier than, for example, in like a valley. Um,
Okay.
so in the Carboniferous period, all of these plants needed a ton of water,
Yeah.
which wasn't a problem in most of the Carboniferous because it was a rainforest ecosystem.
Yeah.
Um, but up toward the top of mountains, there's just less rainfall.
Mhm.
So the most of the rainforesty type plants couldn't live up there.
But that only
Uh,
extended like closer to the coast instead of like in the center of like where Pangea was.
so this was previously during the Carboniferous period.
Oh, okay.
Yep. But once Pangea formed and then things dried out, they were able to come down from the mountains and fill in the spaces that were
Oh,
previously the rainforests. Yep.
all right. I see.
And it's really important to note
Cool.
when talking about plants is that flowering plants did not exist yet. So that would be think of a plant that's not like a pine tree. You're thinking of a flowering plant. Whatever you're thinking of, it's a flowering plant that did not exist yet. So a lot of these places would look very foreign. So they're like things like no grasses. Grasses did not exist yet. Flowers did not exist yet. Fruits, in like the true sense of being a fruit, did not exist yet. Plants were very alien to us, to what we would think of in most of our plant ecosystems. Um, but getting more familiar with these, gymnosperm dominated ecosystems.
So, do you have like a classic example of a plant that would resemble something like this?
So a lot of uh, like your pine trees or like your big tall redwoods would look fairly similar.
Okay.
Um,
But there wasn't
some of
like
them, right?
any like non-tree things.
Yeah, there. I mean, there were some like ferns and
Okay.
mosses and
That's
stuff
what
like
I
that
was
were
thinking. I
around.
was
Yeah,
like, what about
yeah, yeah,
ferns? Cool.
yeah. And we'll circle back to ferns in a little bit.
Cool.
S- But what the Permian's most famous for, other than sort of that those ecological tiering in the shallow marine ecosystems, is the terrestrial stuff. Lots of insects were flying around, including some of the first beetles, which, for reference, are the most diverse group of animals alive today.
Insects are crazy diverse.
And insects are crazy, yeah. Like I think it's like 20% of all species are a beetle.
Wow.
Yeah, it's insane. And also, since we're talking about insects, it's kind of important to note, just for picturing this world in your mind, that the only things that were flying at this point in Earth history were insects. No vertebrates had developed the ability to fly yet.
I guess that would make sense why they're booming.
Yeah. There were some that probably could glide from tree to tree, but no actual flying yet. But so now we get into my personal bias, the tetrapods. So things with arms and legs. Amphibians were still doing their thing. They had been dropping off for the last couple of, dozen million years or so, since things that could come up out of the water evolved. But especially because of how dry things were, amphibians were not doing especially great in the Permian period. Although they did have some really interesting species evolve. One is a genus called Diplocaulus, which is maybe a couple feet long, but its head is like a big old boomerang, and we're not quite
What?
sure why. Yeah. So coming off of the back of its head on either side, it just goes back like past its shoulders, but it's just like a big
Whoa.
point, not like a horn or anything, just like its skull extends backward on either side to make like a boomerang shape. It's very strange.
Okay.
Um, so while most amphibians were not doing great, some of them did get to pretty big sizes, up to like alligator size or so. So some of them were still doing okay, but in general, they were getting sort of pushed out of some of these bigger niches. And that's because amniotes were really running the show. So amniotes are the things that lay shelled eggs. So you think of like fish eggs or frog eggs. They're very gooey and they can't leave the water. Amniotes are the things that lay eggs that can. And so this would be today the groups of reptiles, including birds and mammals, because even though mammals, most of us, don't lay eggs, our ancestors did, and so we're included in this group. Back previously in the Carboniferous period, the two main groups of amniotes split: the reptile side and then the mammal side, which are called synapsids. And both were doing really cool things in the Permian. However, the synapsids were really, they pretty much had the run of the place. Pretty much every major terrestrial niche was occupied by a synapsid. And just for
I
reference,
was
how,
wondering.
yeah.
Sorry.
No,
I'm
that's
gonna
okay.
go back a little bit to
Yeah.
insects. You said that they're
Yeah.
the only flying things in the Permian.
Yep.
So that statement would also imply that there are no flying predators for those insects to
Other
be.
insects.
Oh, okay. Yeah, I forgot about that. Uh,
Yeah. So during the Permian, there were giant dragonflies, and by giant I mean like their wingspan was probably about the length of one of your arms or so.
okay,
So big for an insect.
right.
So and they were probably not even probably they were probably they were the biggest thing flying around on
Yeah.
Earth, and they were dragonflies today are very effective insect predators. So,
Hmm.
uh, so probably was the case back then as well.
Yeah, because I'm just trying to imagine like the uh the I don't loss of words here, but like the way thing who eats what? A food web. There it is. um and if like there's flying insects then and nothing to eat them, then uh what is just like what would be able to cap them as species, but then
Right.
obviously you said dragonflies are going to eat other ones, but then what eats dragonflies?
Well, in that sense, that's they're sort of the apex predator. It's sort of like what eats
Right, okay.
lions.
Yeah.
Um, which the answer is other lions and also anything that can get a hold of a baby. Um,
Yeah.
so, uh, and also if you think of things like frogs, for example, today they eat lots of insects, and I'm
Right.
sure lots of things were able to catch and eat even some of the flying ones. So,
Okay.
um,
Cool.
yeah,
I'm just trying to wrap the whole ecosystem food web
right.
situation up in my head. But
Yeah,
anyway,
the
back.
Permian. No, that's okay. The Permian period and the Paleozoic in general, the ecosystem structures are just very alien to us. After the
Yeah.
Permian period, things get much more familiar looking.
Hmm.
Um, we'll talk about why in a little bit.
Cool.
Um, but yeah, like I said, the synapsids pretty much had the run of the place in terms of vertebrates. And for reference, the Wikipedia page has two whole sentences about what reptiles were doing during the Permian period. Um, so they were around, but not doing a ton of things. Although it is noteworthy that the first archosaurs evolve in the Permian period. So archosaurs being the group of reptiles that includes crocodilians, dinosaurs, and birds.
Ooh.
So they first show up here, but like I said, they were around, but not very diverse or widespread. So Uh, we talk a whole lot about what synapsids are in episodes 35 and 53, where I go through the history of mammal evolution. And so these, especially the early ones, you would look at it and call it a reptile. Even though they technically are not. It's one of those weird taxonomy things.
Yeah.
So, for example, one of the most famous examples to use for this is Dimetrodon. Dimetrodon looks very much similar to like a Komodo dragon, but with a big sail on its back. It's
So,
often... Oh,
Gavin,
good. Yeah.
what is the difference between the reptiles and synapsids?
So the easiest difference is the number of holes in your skull behind your eye.
Okay.
Yeah.
Makes
So again, a
sense.
technical thing. So the reptile side are called diapsids. They have two. And synapsids, I don't know what the root of syn, S-Y-N,
Yeah.
is, but they only have one. So yeah, one side turns into all the reptiles, and then the other side eventually leads to mammals, but that had not happened by this point.
Okay. Thank you.
Yeah. So, like I said, especially the early ones would look quite a lot like it. And in fact, Dimetrodon is very often called a dinosaur because it's a reptilian-looking thing from the past. If you buy like the little set of kids' dinosaurs, like plastic toys that are like one color on top and a different color on the bottom, I think most, people in their, I'd say, mid-20s to early 30s probably know what I'm talking about. That it will include a Dimetrodon. It looks like Spinosaurus, but on four legs. Anyway, very widespread, very abundant, and likely the biggest or one of the biggest predators on the planet at this point. It was, like I said, about the size of a Komodo dragon. No idea really what it was using that big sail for, but it was not the only one with a sail. There were even some herbivorous ones with the big sails along their back. Not quite sure what they were using it for. But speaking of herbivores, synapsids also were some of the first ever large vertebrate herbivores. There'd been some large arthropod herbivores, some like giant centipedes or millipedes previously, but the first vertebrate herbivores were synapsids during the Permian period. Later on in the Permian, a specific group of these synapsids started to show a little bit more mammal-like traits. These are called the therapsids, meaning that they had somewhat differentiated teeth, a more upright posture with the legs more under the body, maybe being warm-blooded partially. Not quite sure on that one, but there's different, lines of evidence for it. And then at the very end of the Permian, a subgroup of those, called cynodonts, split off, and later in the next period, the Triassic, would eventually become the mammals.
Cool.
So all that to say, we're a couple steps removed from mammals, but we're on the way by this point. So that's what the planet was doing. That's what life was doing. And that brings us to the end of the period. And this part of my notes literally just says extinction time.
Yep.
So the End-Permian mass extinction has traditionally been considered one of the quote-unquote big five mass extinctions. That is to say, some of the first people to really look at long-term trends in biodiversity noticed 5 big drops in biodiversity, and this is one of them. Those are not necessarily the biggest, or definitely not the only ones, but the first 5 that were very clearly noticeable.
Yeah.
We've talked about 2 of them before, at the end of the Ordovician, the end of the Devonian. Then there's this one. After this, there's one at the end of the Triassic, and then one at the end of the Cretaceous that killed the dinosaurs. And there have been sort of arguments about whether, like I said, these 5 were the worst 5. For example, the late Devonian extinction, it's sort of been suggested that it was a lack of new species evolving instead of more species going extinct. That could be really hard to tell. but there's different lines of evidence that can support that. You can go back and listen to our episode about that for a little more, but we're a little short on time today, so we're not going to go into that. But there's been lots of arguments about what five really deserve to be the big five. There have been no doubts whether this one deserves to be in the big five. There's really been no doubts that this one is by far the worst one. So,
Jeez.
all of the other extinctions, pretty much, the exact cause has been kind of debated. Even with the end Cretaceous that made all the non-bird dinosaurs go extinct. Yeah, big asteroid hits planet, but there was a lot of other things going on the Earth before that happened that might have made the dinosaurs' life pretty hard. With this one, you know, it's not really a secret what caused this extinction. And it's
So what
interesting.
was it?
So it's kind of interesting. Before I get into the actual extinction itself, there are two other extinctions toward the end of the Permian period that are different from this one. We're not going to go into those today. We can do episodes about those if you want. But they're called Olson's extinction and the End Guadalupean extinction. Again, we can talk about that in a future episode, but they were not the big one. Needless to say, the entire End-Permian was horrible for life in general. So, this extinction was triggered by long-lasting, and by that I mean tens to hundreds of thousands of years, extreme flood basalt volcanism. So what all of that means
English,
is,
please.
yes. So basalt is a type of rock, usually found in the oceans. So for example, the lava that comes out of all the volcanoes in Hawaii, the sort of slow flowing, creepy volcanoes, that is basalt.
Okay.
Instead of the explodey type Mount St. Helens volcanoes, those are not basalt. So, what flood basalt volcanism means, or you'll often hear them as large igneous provinces, are regions of Earth that at one point were covered in constantly erupting volcanoes that were erupting this basaltic lava.
Wow. So it's just like a constant, the floor is lava?
Not quite, but pretty close, yeah.
Okay.
For all intents and purposes, yeah. For about tens to hundreds of thousands of years, the floor is lava. But that only matters if, you know, how big is the floor here? How big of a building are we talking about? Depending on what source you look at, I found sizes ranging quite a lot. I found kind of a middle ground one that says 5 million square kilometers, or for my fellow Americans, about 2 million square miles.
Wow. And how big is the...
Exactly, that's too big. What does that mean? How big is that?
Yeah.
No countries really fall in this kind of size range. Some are much bigger, some are much smaller, which is weird. There's a big drop-off in that area of how big countries are, but it is a bit smaller, not by much, but a bit smaller than Australia or Brazil. Also, for context for my fellow Americans, it is roughly the size of Alaska, Texas, California, Montana, New Mexico, Arizona, Nevada, Colorado, Wyoming, Oregon, Idaho, and Utah and Kansas combined. The 13 largest states.
Wow.
Yeah. So this was...
That's crazy that both of those perspectives made a much different image in my head, because I'm like, Australia and Brazil, like, that's not that big, but then you say all this and I'm like, oh, that's huge.
Yeah. Yeah. And so it's not like, and the reason why I said only kinda to the floor is lava, so it's not like this entire area was constant, just like active, hot flowing lava for that entire amount of time, but there were just a series of eruptions that produced lava over this large of an area for a really long time. So at various points, you could probably walk around spills of lava to get from one side to the other, but, you know, at various points, all of that 2 million square miles was lava. And so when you have that much lava just oozing out of the ground, a lot of bad stuff happens, like
Yep.
really bad. And so the main 4 gases that are problems for life from volcanoes are sulfur dioxide, which dissolves in water to form sulfuric acid, hydrogen sulfide, which is toxic and can also dissolve in water to form an acid, carbon monoxide, which is toxic and also reacts with oxygen in the atmosphere to form ozone, which is also toxic. And lastly, carbon dioxide, which is a very potent greenhouse gas. And all of those things are really bad for life, but we'll notice a lot those acids. Sophia, you do a lot of stuff in the ocean.
Yes.
What
I do.
happens when the ocean turns to acid?
Ah, yes, ocean acidification. uh, this basically means that there's carbon dioxide dissolving into the water column caused by uh, increased levels of carbon dioxide in the atmosphere. And this can lead to, uh, I believe, organisms that are uh, sorry, I'm butchering this, but organisms to like dissolve their shell because of like the change in pH.
Right, because a lot of animals, and even like some single-celled organisms, make their shells out of what is effectively the crusty white stuff that you find in your coffee pot.
Yeah.
And so when you put an acid on it, like you would in your coffee pot, if you put vinegar on it, it dissolves it.
Hmm.
And generally, even during these times, although this probably got pretty close, it wasn't literally dissolving some of the things, but it would make it
Hmm.
harder for them to make their shells than it otherwise would be.
Okay.
So, not quite literally dissolving the shells off of a clam or something,
Hmm.
but it makes it so they have to spend more energy to get the same result. So, just being less energetically efficient, um, and therefore being able to produce less babies and things like that.
Yep.
Also, with volcanoes, they also throw off a lot of ash. Although these kinds of volcanoes don't tend to throw off a ton because they're not the explodey kind. There's some evidence of some of the explodey kind,
Hmm.
also in more scientific terms called pyroclastic, um, in this kind of thing. But they were by far the minority. But
Hmm.
just this much volcanism throws off even some ash. If it's going on for this much time,
Yeah.
that ash can block out the sun and
Ah,
reduces the ability for plants or marine things to do photosynthesis.
yes.
And especially, photosynthetic things in the ocean, all the different single cell things are the primary producers. They're like the floor of the ecosystem.
Hmm.
And a lot of them also happen to make their shells out of the coffee maker white stuff.
Crusties.
Yes, or calcium carbonate, as an adult would call it. Uh, and so they had a real bad time. And
Yeah.
so if the basement of your ecosystem falls out, everything else does horribly.
Yes. That would make
Uh,
sense.
Also adding to this magma from these lavas may have set fire to underground coal beds, releasing even more
Hmm.
CO2 into the atmosphere. So it's sort of thought that the ash blocked out the sun for a little bit. Meanwhile, and that would reduce temperatures a little bit because the ash is sort of blocking out sunlight, reflecting heat back out into space. So temperatures would have dropped a little bit at first. And then when the ash cleared, all the CO2 is in the atmosphere, and then temperatures just jack right up.
Yeah.
And there's also various things that can happen if the oceans warm too much because of this. So there's usually quite a lot of methane frozen at the bottom of the ocean in various places. And in a normal, healthy ecosystem, that stays frozen. But if it warms up too quickly, all that can become freed, and methane is an extremely potent greenhouse gas, so that would have released even more greenhouse gases into the atmosphere, raising temperatures even more. All this to say, in the short term, there would have been less sunlight because of the ash in the atmosphere, which means less food, and also acid rain from all those acidic gases thrown up by the volcano. But in the longer term, global warming from all these greenhouse gases.
Yeah.
So, how did that
And
affect? Oh, go ahead.
when water is warmer, I don't know if this like makes a difference like at a global scale, but when water is warmer, doesn't it hold less like oxygen, uh,
Yeah. Yep.
like
Absolutely.
O2 in the continent? So it would also be anoxic, you would say.
Absolutely. And that would definitely be uh, that would be a big factor. The oceans being warmer, just holding less, and also all of the photosynthetic stuff in the ocean dying,
Right.
the stuff that
Yeah.
produces the oxygen dying. Um,
So bad,
so
bad.
yeah, and the acid one, obviously if you put acid on your skin, that's notable, but it doesn't screw up your entire life.
Mhm.
Uh,
If you get
whereas
suffocated, you're dead.
Yeah, oxygen, that one's pretty straightforward. You
Yeah.
kind of need that. Actually, all animals need that in some
Hmm.
form or another. Um, so yeah, all to say, life was real bad. And
Yeah.
so first, let's talk about
And
the marine
one question.
extinctions. Yeah.
How is there any thoughts about why all of these volcanoes decided to just start spewing this basalt at
So
the same time?
basalt tends to come from really deep within the earth. It
Okay.
tends to have heavier elements in it than say the more pyroclastic Mount St. Helens type ones. Um, and so it could just been that there was a big hotspot that happened to be over a continent, and it would just sat there and built up, and then
Mm.
eventually just started releasing all of it at once. But because it's not the reason why basalt isn't explodey is because that it's actually for being lava. It flows quite well. The reason why the ones that do explode is because they don't flow; they stick. They're very sticky, and so
Mm.
it allows that pressure to get built up. But the basaltic lavas, they can flow a lot easier. Um, so it's sort of like if you let your toothpaste
Like,
harden in the front of the tube, and you squeeze it, and it all comes out at once. That's the non-basaltic lavas. Whereas if
mhm.
you just use toothpaste like a normal human and just gently squeeze it, it'll all just kind of flow. You know what I
Mm.
mean?
Yes.
So that is what did the extinction, but what actually happened to the life? There needs to be the things to go extinct. So we'll start in the oceans, and oh boy, things were real bad.
So sad.
So on the low end, 90-ish% of all species go extinct. And I've seen numbers as high as 95% of all species go extinct.
It hurts. It hurts to hear.
Yeah. So, for reference, those different kinds of corals that were around, completely gone. 100% gone. Brachiopods, extremely close to total extinction. 96% of species. Actually, I think the one that I saw for this was actually genera. So, in terms of
Mm.
species, it would be higher than these numbers. So, 96% of brachiopod genera gone. Crinoids, they get hit really hard and never really recover. 98% of their genera gone.
Jeez.
Gastropods, snails and slugs, 98% of their genera gone. Ammonoids, the swirly shelled squid boys, 97% of them gone. Corals in general, not just the different kinds, but corals altogether, and this includes what we can tell of some of the more soft-bodied ones that don't make the hard skeletons, but 98% of them gone. And even groups like bivalves that didn't get hit super hard still lost 59% of their
Wow.
genera. Yeah. So the lucky ones, only half of them went extinct. So, and all of that, like I said, is just most of those things, those, brachiopods, gastropods, crinoids, ammonoids, all of them make their shell out of some kind of calcium carbonate.
Yeah.
Brachiopods do it a little differently, but the big
But they
thing
were
for
just being
them
suffocated
was
anyway.
right. So they, yeah, pretty much everything in the oceans did atrociously. We
Yeah, I
don't
mean,
super know
there's
what
no
was going
escape.
on. Right, exactly. It's hard to tell what the deep oceans were doing just because we don't have rocks from that.
Yeah.
But I think it's pretty safe to say that it was also pretty bad there too.
Mm.
So on land, things were a little less of a literal apocalypse, um, but it was still pretty bad.
Yeah. Well, why? What gave land more of an advantage, I guess, than marine for biodiversity loss?
Hmm. I think the biggest thing is that their entire environment wasn't trying to kill them.
Right. Okay.
Acid rain is detrimental to your health,
Hmm.
but our calcium is on the inside, so uh, it doesn't immediately try to kill us like
And
it would for
us,
things that
who are you
make shells.
talking about?
Us, as in, like things like vertebrates.
Okay.
Um, so that's probably the biggest reason. Also, there were just generally more resources on land. Um, so plants were hit really hard, but only on sort of one front. The blocking out of the sun was really bad for them, but they came back. Also, plant seeds are very robust and sturdy, so they were able to bounce back fairly quickly. Whereas things in the ocean were being, the photosynthetic things, like I said, they're being attacked by the acid, so they can't make their shells. The sunlight is also being blocked out, and they also don't make seeds, so they are much less, resistant to these kinds of changes. And also, speaking of those ferns that I mentioned earlier, there's a big fern spike at this point. So ferns are really popular, like succession species. After things get real bad, ferns are usually the first ones that come in because they can grow really fast.
Yeah.
Which is why if you see like a big forest fire, ferns do great immediately after a forest fire. Because they can grow really quickly and they can live pretty much anywhere as long as there's like a decent amount of water. So in some of these, especially the more coastal areas, ferns did great.
So
And then they sort
what
of
you're
paved the way for the trees to come back.
what you're saying is like these types of organisms aren't dependent on their parents being alive when they start to grow again, right?
Yeah, I think
Whereas
that's a good way
like
to put
with
it. Especially mostly the plants. And as long as
yeah,
there are plants to eat, the things on land will be mostly fine.
yeah. I guess I just meant like in comparison to like the marine life,
Right.
they needed the living like parents to kind of keep things going.
Yeah, absolutely.
Cool.
But like I said, even though things were better on land, that doesn't mean things were good.
Yeah.
So this was the only mass extinction to really put a dent in insects. Insects have
And
been around for at least 4 of the big 5, maybe the 5th. They actually no, they were, I don't know if they were true insects, but there were arthropods on land that were very insect-like. So I'm going to go ahead and say that they were on land for all 5 of the big 5, and this was the only one that we can tell really affected them. And that primarily is probably because of their relationship with plants. Plants have a weird relationship with mass extinctions that they tend to bounce back very quickly. And so if the plants are doing okay, insects are probably also doing okay. But the fact
Yeah.
that this one, like you said, insects are crazy. So if this was the one that put a dent in the insects, it's saying something.
Right. Yeah.
Plant diversity is kind of hard to measure because plant fossils are very hit or miss. But the ecosystem structure changed a whole lot. Like I said, immediately afterward, less conifers, more ferns, but then the conifers come back with some more new forms to play with, ones that are more similar to the kinds of conifers that we have today. In the vertebrate side of things, about 2/3 of all species go extinct. So, like I said, better, but still not good.
Definitely not good.
Yeah. Most of these synapsids go away. All of those things that are reptile-y, but more close, on the way to mammals, most of those go extinct. All of the very non-mammally ones go extinct. Special shout out to a particular genus called Lystrosaurus, which was a synapsid who did actually amazing during this extinction. In certain areas, Lystrosaurus makes up 90% of all the fossils found immediately
Wow.
post-extinction. Yep.
Uh, are
Um,
they like, do they have some sort of like physical structural advantage that is possible?
Not particularly. Um, so
See.
Lystrosaurus is maybe like a medium to smallish dog-sized synapsid with a beak and some these sort of tusks on the side. Um, it's been sort of hypothesized that it might have been like a root specialist. So it's
Okay.
like, well, if all the trees die, the roots are still kind of there. That's I didn't look super hard into Lystrosaurus. I just know that it's funny,
Yeah.
like comical
Yep.
how well it did compared to everything else.
Right.
Um, and all in all, in this extinction, life had shifted enough, like I said at the beginning, for those early scientists to recognize it as the end of a literal era. And after the extinction, we leave the Paleozoic era behind and head into the Mesozoic era and the Triassic period. The Mesozoic era is where all of the dinosaurs are from, and very commonly called the Age of Reptiles, because after this, the synapsids sort of lose their prominence, and all those archosaurs that I mentioned earlier start to fill in some of the roles that these synapsids left behind.
Nice. So, Gavin, I have a deeper question for you. Uh,
Yeah.
After something like so big like this happens, like in terms of loss of biodiversity, like how does life recover after like these mass extinctions?
So that's a really tough question.
Hmm.
Most of it is, you know, when all of these things die. So say for example, you say you are a kind of bivalve and
Hmm.
can make your shell while using 0.5% less energy than some of the other bivalves around you. In this particular
Okay.
scenario, in the normal world, that wouldn't matter, right? That's just a
Right.
random thing. Cool, man. But in this scenario, where everybody's having a really hard time making your shells, that makes you able to put more energy into making babies, which is the end goal to evolution. That's how evolution happens, is making babies.
Yeah.
And so if that allows you to survive, all of your competition goes extinct, which
Hmm.
means that there's, and even though they were competing with you, they're slightly different than you, meaning that there's now room to become slightly different, opening up more
Okay.
niches. And
Yeah.
so, that is true for basically every kind of life. Is that once things go extinct, new things can evolve to take the place of doing similar-ish things to what just went extinct. And the main ingredient there is time. For
Okay.
example, depending on what group you look at, it took anywhere from 15 to 20. I've seen maybe on the low end people say 10 million years, but somewhere in the ballpark of 10 to 20 million years after this. I've even seen some people say that the world didn't really recover until the mid Triassic, so almost 30 million years
Wow.
after this. And you can even kind of make an argument that uh, the world still hasn't fully recovered yet, because some of our ecosystem structures are more simple today than they were back then.
Right.
So even here we are 252 million years later, and there's a not unreasonable argument that we still have not really recovered from this event.
Hmm.
So
Cool.
one last thing that I'd like to talk about is some notes about modern climate change, because this
Hey.
event has been studied quite a lot to try and learn some things about our modern climate, because it's
Hmm.
not that hard to draw comparisons between this event, which spewed a whole bunch of greenhouse gases into the atmosphere, to today, primarily about the carbon dioxide. And
Yeah.
this isn't the only time that this has happened. In episode 32, we talked about the Paleocene-Eocene thermal maximum, which was a time somewhere in the ballpark of 50 million years ago or so, where things got real hot real fast. But it was already hot when that happened. Whereas in the Permian period, it was generally fairly cool when, right before it got real hot. And generally, the world is fairly cool right now, and it's about to get real, real hot. But just a little
Yeah.
context for how hot it got then versus now. Temperatures in the End-Permian jumped by anywhere from 6 to 10 degrees Celsius. And this is what happened. 95% of marine species going extinct because of 6 to 10 degrees of climate change. We are very concerned, extremely concerned over 2 degrees Celsius.
Hmm.
But it's a big matter of magnitude versus rate. That's the big thing that anytime I talk about climate change is you have to explain the difference between magnitude and rate. Because yeah, in the End-Permian, it jumped 6 to 10 degrees Celsius. But that happened over minimum a few dozen thousand years.
Okay.
So we're jumping 2 degrees in about 200, we'll say 300 years tops.
Okay.
So the magnitude of the End-Permian is bigger, but the rate for today is much higher.
Yes.
And so the analogy that I give when talking about rate versus magnitude is, if you go, say you're in a car and you go 0 to 100 miles per hour, but you do it over the course of like 10 minutes, you're not really going to feel that.
Hmm.
But if you go the same magnitude, 0 to 100 in a second, that'll probably kill you. Same magnitude
Right.
of speed change, but the rate is much different.
Hmm.
So, not a super happy note to end on, that
Yeah.
we're on pace to be beating the worst mass extinction in Earth's history.
Right.
But
I would like
election
to.
season's coming up here in the U.S., and vote for pro-climate legislators, please. Thanks.
Yeah. I also would like to add some less happy things on top of climate change that we're also dealing with, like right now, in terms of extinction, and that's like the amount of habitat loss and over exploitation that we have, that's just adding the cherry on top. It's like you were saying, how there's multiple factors that were making things really bad for marine life. And extinction time, these things too are also just adding to the concern.
Yeah. So, like I said, election season is 10 weeks away as of yesterday, the day this episode comes out. Vote for pro-climate legislators. That is the official stance of this podcast. So, this has been episode 89 of I Wish You Were Dead, a podcast about things that used to be alive. In this case, many things that used to be alive. I have been Gavin. That has been Fia. And we will see you all next week. This episode of I Wish You Were Dead was written by Gavin Davidson and hosted by Gavin Davidson, Mike Bryson, and Fenella Campanino. It was sound edited and edited for YouTube by Gavin Davidson. Special thanks to former guests of the pod and to listeners like you.